done his PhD from Cornell, then worked at Caltech as a postdoc, and since then has been a professor at Cornell University. He works on compact objects, accretion disk, exoplanets, probably many other things that I forget about, and today he's going to talk about dynamical binaries.
Okay, good. So thank you. So it's always a pleasure to be here. So I want to talk about three topics related to tides and binaries. The first one dealing with compact white dwarf binaries in circular orbit, merging due to gravitational radiation. Eventually they're going to merge, but we're interested in tidal interaction before they merge. The second one concerns this very interesting main sequence of binary systems, Kepler KO-4. It's an eccentric binary. There are some very interesting dynamics that's apparently have been detected. So we'll talk about that also. And the third topic concerns the exoplanetary systems in inclined orbit, hot Jupiter in inclined orbit with respect to the spin of the star. Okay, so it's an inclined orbit. Okay. To begin, let me quickly remind you, for those of you who do not usually do this kind of thing, I just want to say that tides is an old topic in astronomy. Okay? The traditional ways of looking at tides, it's just based on the so-called equilibrium tide theory, okay? More than 100 years old. Okay? The equilibrium tide corresponds to the global quadrupolar deformation of the star. Now, because the star has finite viscosity, it has dissipation inside the star, okay? There's a tidal lag between the tidal bulge and the line joining the two stars. Okay, the tidal lag. And this is called tidal lag angle. And this tidal lag angle is always usually parameterized. Okay, it's proportional to the tidal forcing frequency, which in the case of circular orbit is simply the difference between the orbital frequency and the spin frequency of the star times 2 because quadrupole. Okay, so the tidal lag angle is basically the tidal forcing frequency times a lag time, which depends on viscosity. Because very viscous fluid will be big lag angle. Okay, and this lag angle is roughly speaking proportional to inversely proportional to the tidal Q parameter, the quality factor of the sort of fluid. Okay. So that's, we can parameterize this lag angle either by lag time or angle or this Q factor. Okay? That's what people usually do in this kind of discussion. So once you have a prescription or parameterization for the lag angle, you can then easily estimate the tidal torque, interaction torque between the perturber or the secondary star and the primary star. That's basically simple scaling, depending on the mass of the perturber and prime, inversely proportional to the separation of the major axis to the 1/8 to the 6th power, and directly depend on the lag angle. Okay? So once you have this torque, you can of course then calculate or study the evolution of the binary system, including the spin, how the spin evolved, and so on. So that's how you usually discuss this tidal problem. For many years, this is of course very useful because it allows you to do a lot of calculations in a parameterized way. But of course, it also has been long been recognized that this equilibrium tide theory has a lot of problems. This problem has been well recognized in the literature. The first problem, of course, is that it's parameterized theory. Right? All the uncertainties about the fluid, the dissipation in the fluid, is parameterized by this Q factor or lag angle and so on. It's parameterized theory. And the second problem with that is that the problem with this equilibrium tide theory is that this, in almost all the physics, almost all cases we are dealing with, many situations, the physics of tidal dissipation is much more complicated than this quadrupolar deformation. Okay? In addition to this quadrupolar deformation, there are many other interesting dynamics that may be happening inside the star in the fluid. Okay? And in particular, you could have excitation damping of the internal waves inside the star, or oscillation modes inside the star. This is what we call generically called dynamical tides. Okay. So this is not just this quadruple global deformation, but rather you excite waves or oscillation modes inside the star. Okay. Much more complicated, much more interesting than this quadrupolar deformation. So I should say that over the years, there have been a large body of theoretical works devoted to understanding different aspects of dynamical tides in different kinds of systems, ranging from massive stars to planets. Okay. Yanqing did some work some years ago looking at the inertial waves, cycling inertial waves. Okay. So I will not be able to do justice to try to review. I'm not going to make any attempt to try to review this large body of theoretical works. Instead, I'm going to just concentrate on this, some of the recent work we have been doing on these three subjects I mentioned earlier. And the final problem with this equilibrium tide theory is that for some applications, and this parameterization may actually give you misleading results. So you may take the attitude that, yeah, if the physics of Q or tidal lag and it's very messy, but I'm going to take an empirical approach, make this parameterization and be happy and apply it. But I'm going to try to convince you that for some applications, this parameterization may not be adequate and give you a misleading result. Okay. So with that introduction, let me move on to the first topic, okay, concerning compact white dwarf binaries. Two white dwarfs orbiting each other in circular orbit, typical periods ranging from minutes to hour, 1 hour or so. So these are basically merging white dwarf binary systems. The orbits are shrinking due to gravitational radiation, so eventually they're going to merge. Okay? And these systems are interesting because when they merge, they may give rise to many interesting things, right? Such as type 1a supernova, transients, or something may happen. The AIC, when they merge, the mass is bigger than the Chandrasekhar limit, you may give rise to you may form a neutron star through the process of AIC accretion-induced collapse. Okay? So that's why these kind of systems are interesting. Okay? Of course, there's still a big debate concerning what's the origin of type 1a supernovae, right? And whether single degenerate scenario, double white dwarf merger, whether sub-Chandrasekhar mass or super-Chandrasekhar mass. Okay, we should ask Martin and Cooper about this. Okay? And another interest for this kind of system are interesting because they generate rotational waves that may someday be detected by the space-based interferometer, LISA. I don't know when this will happen, but someday it may happen. So that's why these systems are interesting. And as I mentioned, these systems have been detected over the last, especially the last few years. There are a number of surveys, ongoing surveys, trying to detect many of these kind of compact white dwarf binary systems. Here is just one example from last year, and there's a 12-minute double white dwarf binary system, eclipsing, double eclipsing, one dip, two dip, different two dips, so there's two eclipses, double eclipses within one orbit. And we see all kinds of interesting things, classical binary phenomena. Okay? And the period is very short. That means that the binary will merge within a million years lifetime. And eventually they're going to merge. And they're going to generate rotational waves. You observe that LISA is there. And the optical decay can be measured by timing, by doing precise measurement of the timing of the eclipse. So these kind of systems certainly exist, they are being found. So with that motivation and background, with the student Jim Fuller, we started this project and trying to understand the physics of physics of tides in this kind of merging white dwarf binary systems. And the issue we're interested in are the following. The first, we want to know when the orbit shrinks, the orbital frequency of course increases, right? And can the white dwarf be synchronized with the orbit? Spin frequency will try to be equal to the orbital frequency. Can that happen? Okay. Right? It's not obvious because the orbit is shrinking very fast, faster and faster as orbit decay, right? So it's not clear whether the tide can compete with the gradually increasing orbital decay rate. So we want to know whether the orbit spin of the white dwarf is synchronized or not. And this is relevant because if you try to want to understand the merger product of the white dwarf, when they finally merge, and that clearly matters whether it's synchronized or not synchronized. So that's one issue we're interested in. Another issue is, of course, before they merge, there's tidal dissipation in the white dwarf. We'd like to know whether how significant is the tidal dissipation can happen inside the star in the white dwarf. Okay, can the white dwarf become bright before they merge due to tidal dissipation? And finally, this tidal interaction can also affect orbital decay rate, because if you transfer the orbital energy to the heating, to the spin energy of the white dwarf, the orbit will decay faster than you would predict. You would predict by just point mass decaying by rotation radiation. Right? So that's another motivation for this. Okay, so we want to look at the physics of tides in this kind of system. Now, in order to look at the dynamical tides inside the white dwarf, we have to look at the structure of the white dwarf a little bit. Okay. So here is the so-called propagation diagram of white dwarf. So for those of you who know this is very familiar. If you haven't seen this before, then you just ask you to concentrate on this line. This line is N, called Wasala frequency. It's basically a measure of the buoyancy inside the white dwarf. So when N is finite, positive, that means if you take a fluid element inside the white dwarf, if you perturb it, it's going to oscillate. And that oscillation is basically the gravity wave, basically. And so you see that this is a finite N, that means there can be gravity wave inside the white dwarf. Okay? And you can see features here, spikes. In this particular white dwarf, 1.6 solar mass white dwarf. This is a carbon white dwarf for the central regions, carbon oxygen, surrounded by helium shell and then hydrogen shell. So these spikes correspond to transition between composition transition, basically. We transition from carbon oxygen to helium, from helium to hydrogen. Okay? These features will be important for the excitation of gravity wave in this system. And here is just another white dwarf model. It's very different because it only has helium white dwarf, okay? Helium core and hydrogen shell, hydrogen envelope. Okay, so as I said, because this is finite, that means you could have a cavity inside the white dwarf. And this cavity, that means you can have a standing gravity wave, or G mode, can exist inside the white dwarf, right? Okay, you have standing gravity wave or G mode inside the white dwarf. So the first thing one should think about is whether this G mode can be excited, or how this discrete G mode can be excited by the tidal interaction, by the tidal potential. Okay? So the picture that is following, we have this inside this white dwarf, we have this harmonic oscillator G mode, has some frequency, omega alpha. So alpha is the index for the mode. So this is the intrinsic mode frequency of the white dwarf, right? The mode. And the orbit is decaying gradually, driven by rotation radiation, shrinking. So the tidal forcing frequency, as I said, is just twice of the difference between the spin frequency and the orbital frequency. So as the orbit shrinks, the forcing frequency goes up. So at some point, the forcing frequency will sweep through this intrinsic frequency, right? So therefore, this mode may be excited. Right? So that's a well-defined problem. You have harmonic oscillator sitting there, external forcing, with gradually increasing forcing frequency. So it will transfer energy, so resonance can occur. Okay? So when this happens, when the orbital frequency is such that the tidal frequency matches the intrinsic frequency of the mode, you can have resonance. When that happens, you transfer orbital energy to the mode energy. Mode gets excited. So that can be calculated in a well-defined way. It's a very clean problem. And what you have to do is look at the combined evolution of the mode oscillation or the amplitude of the mode evolve, and at the same time also keep track of how the orbit evolves, because when you transfer energy from orbit to the mode, the orbit is losing energy, so you have to keep track of both. Okay? So this has been done. Here's just an example. So here is the mode amplitude in some dimensionless units. You can see initially it's gradually increasing, and then encounter this resonance, it suddenly shoot up and oscillating because it's still interacting with the tidal potential. At the same time, orbital radius increases gradually, and then at this resonance, you suddenly transfer a lot of energy from the orbit to the star. So that's what's happening. Now, the result, unfortunately, the result of this clean calculation is that what we find is that this resonance is very strong, in the sense that even though the mass average amplitude, you try to define sort of the mass average amplitude of the mode, that amplitude is very small, like 10%, 3%. But because this white dwarf, this C mode, gravity waves, they are mainly concentrated. Most of the waves is actually concentrated in the envelope of the star. So what you find is that the displacement of oscillation, of the induced excited oscillation, is actually very large, comparable to the stellar radius, or even larger. So that means, of course, this whole picture is not quite right, because you can't have such a large amplitude. What will happen is that if you excite this mode, the wave becomes very large amplitude at the other surface. So the wave cannot bounce back, reflect back, right? So in order to get standing wave, what you need is to have wave bouncing back and forth between two boundaries, the inside and the surface bouncing back and forth. That's how you get standing wave. But because the mode amplitude is so large, we don't think you can have this standing wave forming, because the outer boundary is highly dissipated because the wave becomes nonlinear. Okay? So the surface displacement become very large, so there are a lot of dissipation, nonlinear effect, and therefore we don't think there should be a standing wave. So therefore this is not the right way to think about this problem. So that's the first thing we did. It's not the right way to think about this problem. You don't get discrete, you don't excite discrete G mode in the wave group. Instead, the right way to think about this problem is that you have continuous excitation of gravity wave inside the white dwarf, in the interior of the envelope of the white dwarf. You basically tidal forcing, tidal potential excited wave in the inside of the white dwarf, and this wave propagate outwards. And when the wave propagate outwards, it don't come back. Nothing will make it come back, right? Because the wave propagate outwards, the amplitude becomes very large, and it will be damped or dissipated. So wave generated excited from the interior or envelope propagate outwards and then dissipate near the surface. So that's the right way. That's the right way to think about this problem. And this can also be calculated. So here's an example. Here's one particular white dwarf being forced by a companion star with a given forcing frequency, so a given orbital period. Let's say, right? A given orbital period, here we find the forcing frequency. So you can see this companion tidal potential excite a wave train of gravity waves. This wave mostly small amplitude, and then near this near this region, some region of the white dwarf suddenly become large.
You still get this discrete spectrum of gravity waves.
In what sense?
Well, in order to get the resonance, you need the discrete spectrum.
In the previous picture?
Well, in the previous picture you had a cavity.
Yeah.
You have a discrete spectrum.
Yeah, discrete spectrum, yes. Here, I don't assume there's discrete spectrum.
But you still get, okay, so you don't get a resonance, you just like
you still get feature, then come back. You'll see the next part. You'll see it. Okay. So this is for one particular thing. Just choose some forcing frequency, right? For orbital period. It's wave train being excited and then become large. And this wave, of course, carry energy or carry angular momentum. So you plot the energy flux carried by the wave. In the interior, of course, just positive, negative, because just less. But then going to the outside, you get a net outgoing energy flux. And eventually this energy flux will dissipate near the surface. So you can see here, most of this change, sudden change in energy flux of the wave occurs at this particular region where we have the transition from carbon oxygen to helium. So this green curve is this one of the Oscillations because you see the feature here. So wave excitation may occur here. We have a feature.
Wave excitation like that?
Well, for whatever reason, the wave get launched here in this region. But of course, the dissipation, the perturbation everywhere, right? All this region is wave zone, right? All this region is wave zone. But most of the change somehow occurs here. Because it's this feature, this region where the feature sudden change in the ground Oscillations frequency. So this is for one particular, just one example for a given forcing frequency, tidal forcing frequency. So now we can do the same thing for, look at the energy dissipation, energy flux, or angular momentum flux, as a function of the forcing frequency. We can do this for different forcing frequency. Okay. And here is the result. So this tidal torque is basically the angular momentum flux carried by the outgoing wave, traveling outward, right? The energy travel outward, they get dissipated. So this is basically energy, tidal energy transfer rate from companion to the star, to the tidal process. Corresponding to this energy flux, there's a torque, of course, right? There's this related to each other. So this is tidal torque carried by the wave. So basically, tidal torque transferred from the companion perturber to the star. And I'm plotting this as a function of the forcing frequency, the tidal forcing frequency, in some dimensional units. This is units in units when the mass and the mass of the star equals 1 and the radius equals 1. So I'm plotting this dimensionless function f of omega. You can see here, this is if you go back to my first slide and just go back. So I mentioned before here, right, the tidal torque is just this dimensional quantity, and you get an estimate times the lag angle, the dimensionless lag angle. So this function f here is now, it's not a parameterized now, it's basically, it's just the lag angle, effective lag angle, except now it's calculated based on the theory. Okay? So calculated lag angle.
It's basically calculated assuming the wave completely dissipates.
Exactly. So basically this wave outgoing, we just assume that once it's outgoing, it will eventually damp. Right? This wave is gone. Once it's outgoing, it's never coming back.
Okay, so the surface, is that it?
It's deposited near the surface, somewhere near the surface. Outermost region of the
By
wave.
assumption.
Right. Right. The reason we justify this is because for each of these frequencies we check, you can see the wave will become nonlinear if you let it propagate outwards. Because when the wave propagates to the low density region, the amplitude will increase. And at some point, the wave amplitude will become so large that it will become nonlinear. Okay, so that is the assumption that the assume all this outgoing wave is gone. It's deposited in the star.
How much heating will it?
Sorry. No question?
How much heating will it be?
We'll come back to this. Okay, so here it's just the right, so basically tidal torque carried by the wave as a function of forcing frequency. It's kind of a busy plot because we're trying to spend a lot of time trying to understand the result, but just look at the solid curve and all the features, spiky features, so that's the result. It's not a smooth function. It has all the spiky features. If you wish, this f, again, this dimensional function is basically the lag angle inverse of Q, tidal Q. So that gives you a rough idea, right? The tidal Q factor is 76 here.
This is roughly because you have these discrete surfaces in the star.
Okay, so why this is oscillatory? Why is it oscillatory? Why you have this rather nasty looking features? Why it's not smooth? The reason for this, we think, is that despite the fact that we think the outgoing wave, no local cavity, right? Because no wave is going out, because the assume is gone, outgoing outward. There are features in this propagation diagram, and you get quasi-cavity inside the star. So you can, for example, when you have a jump in the Basala frequency, you have this quasi-cavity. So even though in the strict sense it's not a bump, you don't get complete reflection wave coming in, you don't completely reflect it. Nevertheless, you get some partial reflection. Okay? Right? So you get this quasi-cavity, so at some frequency of the forcing frequency, you can happen to match certain integer number of wave numbers to this little quasi-cavity, and that's the origin of this of the spikes. Okay? So it's not due to these spikes or these features. It's not due to the fact that you have discrete modes, global modes inside the white dwarf, but rather because you have all these features, quasi-cavity inside the white dwarf. Okay.
And actually, excitation region. The excitation region is a finite radial width.
Here.
Right.
Yeah.
If you set it to be like 0 width, what will happen?
We do 0 width.
Because you're saying that's all the excitation happening in that little.
It's
spot.
mostly happening there. Yeah. In fact, we derive some analytical expression based on 0 widths. 0 width sudden change.
But there is no excitation.
Yeah, you can actually derive some of these things, some of the dash line based on the CITA. But this solid line is the numerical calculation to solve this inhomogeneous wave equation. So the precise widths don't matter too much. And of course, yeah. All right. So that's, and here's some other examples. So different stars, you go to low mass, you go to low mass star, helium white dwarf with Q, you can see it's very different. Just look at the magnitude of F. Again, it's the inverse of Q, if you wish. Right? For helium white dwarf, this Q you can see at forcing frequency of 0.1, something to 8. There is this kind of star 4. So it's actually the effective Q, which depends strongly on the internal structure of the white dwarf. Okay, not only this feature, but also all this envelope of this the amplitude of this function is strongly on the property of the white dwarf. Okay, so that's the physics of.
So is it easy to understand? Because in both cases the envelopes are actually pretty thick, so I would have thought it would be not such a big difference. Is it easy to understand?
We think the difference is that in this case you have this carbon oxygen helium condition that we from here. This one's here's the helium core and oxygen was smaller, and it's very hard to make analytical theory. We try to simplify this thing.
Yeah, you think that hydrogen
I don't know.
a bigger change?
I can't give you a simple answer. Why is it much smaller? I can't give you.
Well, the partial reflection is worse in the lower case, right? Because the upper case is a higher partial reflection.
Yeah.
So the wave can travel multiple times in the cavity before it leaks out.
That's right. But so, I mean, this is a inhomogeneous equation.
No, but if it's a partial reflection, if there's no partial reflection, you don't get any of these intensities, right?
You don't get any intensity yet.
So it's very important. It has to be on the partial reflection coefficient, which is stronger than the carbon and oxygen.
Sure. But to excite the wave, you know you need some region where the wave, sort of the wavelength is long, the tidal potential is smooth, right? The excitation depends on the overlap between the wave and the tidal forcing potential, which is smooth thing. So you have an overlap between the oscillatory thing and the smooth thing. And so most of this actually is definitely, but not even excitation.
So if I simplify this even more, so
yeah.
I have a outer layer of the star where square root of G rho is the orbital frequency, basically.
Outer layer of this
star where square root of G rho is the orbital frequency.
So,
Is that where the wave excitation mainly takes place? Or?
I don't know. I can't give you a simple answer. Why is this much smaller?
Yeah,
I can't give you a simple answer. Why is this much smaller?
I
No, I don't think so. It's coming from this example. You can see it's supposedly.
Well, I see a radius, but I don't know what square G rho is there.
Oh, I see. Square G rho. I don't know. Maybe you have an insight.
Compared to this Resonant.
Yeah, here's one result. You can see.
I think that was that.
Yeah, so this has no. So it's one. So the fourth increase is quite old one. And the ground frequency here jumps from one to the other. I don't know if you have a better analytical understanding. It's a very simple wave equation, inhomogeneous wave equation. Just have to solve it with this nasty background.
So how realistic is this damping assumption that you put in? Because stars pulsate and they don't heat themselves to
But
bits.
usually they're not that high amplitude. They're not that high.
And how do you know that the amplitude between, don't you assume that the amplitude is higher? I guess you don't, right?
We have this amplitude here. We can check whether the wave propagate keep going outward. At what point it will become nonlinear?
Right.
It's always get nonlinear. So
But
before being reflected, well,
okay,
you
okay,
have that
sure.
you want
No, I
to
see
be
what
reflected
you're
at that
saying.
point.
Yeah. Because
So-
exactly, right. They always become linear if you go.
Keep going, yes.
So that depends on the mass of the companion.
Depends on the mass of the companion in the linear way, of course, just right. And yes, yes.
It depends on the action of the convection zone.
Depends on the action. Yes, if you have a convection zone here, then
Somehow dumping of energy makes locally convection.
yeah, we have not considered about that, but yes.
Suddenly reduce the wave.
Yeah, if eventually, Yanqing was saying, when you dump a lot of energy in the envelope of the star, you may modify the structure of the star. And then, of course,
Right, and
then you have to reduce
Growth by Zala go to
yes.
minus. For
Right. So, in that sense, this is an assumption that should be checked and keep in mind. This is only the first step. You're right. This is sort of in a way, it's overestimating. I would say overestimating the dissipation. In reality, you could have something maybe partially reflected. So, so in that sense, yes.
Do we know the internal structure of what works well and do therefore well, or is that just
Empirically, Martin can correct. Empirically, I don't think we know.
Well, no, I would say white dwarfs are the best understood objects we have in the universe. So,
But no empirical concentration on the cube, of course.
not on Q, but on the structure.
Structure.
Yes, I would say so. Not
Right.
huge, strong.
Right. This structure is computed by people who make living these Montreal people got this model. Some other models coming from Mesa code. Martin says it's reliable. I believe it. It's reliable. Okay. Right. Okay. So that's the physics of how the wave is excited and get dissipated in an envelope, and the tidal torque. Okay. Now, with this tidal torque, we can now look at, despite all the uncertainty, there's some assumption. Let's just take that, right? Take this tidal torque, computed tidal torque. We can then look at the problem of tidal heating and the synchronization issue. Okay, so for example,
So before you go there, so in principle, I think you already drew some green lines. It does look like you can basically ignore this bumps, or is that unfair?
the green line is just the envelope. So I meant to say that this envelope is not the orbital to the small orbital to the fixed power. So it's very different from the equilibrium pi. Even the scaling, the only about envelope, the orbital to the fixed is 6 power. Okay, so we can now look at the spin orbit synchronization problem, right? Looking at how so again, as the orbit shrinks, the orbital frequency is going up, right? We would like to know whether the tidal torque is acting from the companion to the spin of the star. So the star will try to spin up. So we'd like to know whether the spin up torque is large enough to effectively synchronize the spin of the star. We can basically look at how the thing evolves, right? So the spin frequency evolves because of the tidal torque. And the orbit is evolving because of gravitational radiation still. And And here's a curve. You can calculate this thing. You find that there is a critical, so when the orbital period is larger than, let's say, 50 minutes, the tidal torque is very inefficient, not surprising because separation is large, right? But of course, as you get closer, the tidal torque becomes stronger, it's larger, more efficient than the gravitational radiation, trying to shrink the orbit. So at some point, we'll be trying to be synchronized, and here is how it will evolve. Spin frequency divided orbital frequency. You can see a large orbital period, where the spinning basically is slow. And when you get closer, it's synchronized. And there is a critical frequency at which, we call that omega C, the critical frequency at which the tidal spin up rate becomes comparable to the orbital increase rate, the orbital frequency increase rate. Okay? And that's the point where the spin up becomes very efficient. Okay? So the bottom line here is that if you're looking at binary with periods for 12 minutes, 20 minutes, you will be in the process of being synchronized but not completely.
That's where you're, because now there was a factor 10 to the 4 difference in Q between helium and CO, right?
Yeah, so these are different, these are different models, stellar models, I don't know which is which. And as star try to synchronize, of course, the energy transfer also from orbit to star. So the energy transfer is being transferred from orbit. So therefore, optical decay rate is being modified also. Okay. And then the final thing is you want to know the heating rate, right? So most of the energy. So in this step, in this stage, when the optical period is pretty short, and the star is being synchronized, the energy transfer rate is actually quite simple. Actually, it's given by this simple expression for the inertia of the frequency divided by rotational. Basically, it's driven by this rotational radiation. The star is trying to catch up with the decaying orbit, increasing orbital frequency, and so that constantly there's a well-defined rate of energy transfer. But most of this energy transfer is actually going to the spin energy of the star, right? So only a small fraction going to heat. Right? The heating rate is actually this. So here is basically the power luminosity, a function of the period. You can see the gravitational radiation power is always largest. Optical decay is always driven by gravitational radiation. And then in the earlier stage, when optical period is large, you have this highly erratic thing. Energy transfer, the star is not yet synchronized at all, right? And then when you reach critical frequency, that's where this happens. The energy transfer rate becomes very clean, and then here is the heating rate. Okay,
so why is the heating not sort of half the tidal energy? Because I thought usually for big
it's not this.
You get this. Don't you get half that goes into rotation and half that goes into heat? Or if you're very well away from synchronization?
No, this is look, if you're very far away from synchronization, all the heat, all the energy transfer go to the.
Well, some has to go into rotational energy, right?
This is that formula actually easily like that.
So what goes into rotational energy then?
Well, so right.
The other half, I guess.
The other thing, right? So tide. So E, yeah, so E, one part is going to this. The other part is going to the heat.
Yeah.
Waveforms are spinning very slowly.
Initially.
Yes.
Initially, it's very slow.
So, all the spin is 0.
So I'm assuming it's 0. That's it.
And it can't be if you don't care. It's transferring angular momentum too, so the thing must be spinning now.
It is spinning up, it's not efficient, right? Yeah, that's initially, it's because it's decaying so fast.
Goes as the angular squared.
Right. Initially, At large period, this omega S dot is very small.
Okay.
And this actually is exactly the case. Okay, so that's the total heating rate, total energy that deposited into heat into the white dwarf. Now in this big, well, this when you are like 10 minutes, this can be roughly solar luminosity. So, okay, which for white dwarf is quite large actually, quite significant. So what's the consequence of the tidal heating? And that's actually not clear at this point. We're still working on this. That depends crucially on where the heat is deposited. Okay, I said it's deposited in the outer region or outer layer of the white dwarf, but exactly where matters. Exactly where the heat is deposited matters. Okay. For example, if you deposit the heat in a very shallow region, all this heat will come out as photon luminosity. In that case, the effective temperature will increase, so the star will become very bright. On the other hand, if you deposit the heat deeper, still in the outer layer but somewhat deep, in that case, the thermal time of that layer is long compared to optical decay time. That means the heat you deposit there does not have time to come out. It just accumulate there. It's just they merge. Okay, in that case, you don't see this as a photon luminosity. Okay, so Jim has been playing with this with NASA code to try to put in this heat in different places, and we don't have a clear answer yet. But he did find. He did find in some cases if you deposit the heat in some deep layer, then one interesting thing that can happen is that can actually be nuclear flash, thermonuclear round. You basically accumulate heat at a given place. Right? This is with no accretion. This is like no accretion. Usually thermonuclear round wave happens when you have an accretion. Right? Here is no accretion. You just deposit heat in some region, and then the heat accumulates there, and then at some point it will have suddenly nuclear flash. Okay?
You also have very strong magnetic fields.
No magnetic field. No magnetic
You
field.
can make magnetic fields, right?
That's only in the merger.
You will have magnetic field. I don't know what they have magnetic
Well,
field.
because most report in your one outer part. I mean, the whole thing is differentially loaded. And it's sure it's strong magnetic field.
Okay, that's the next thing you.
I mean,
Magnet dwarf.
if you want to have it, I mean, all the heat in your model is only in the outside, right? So if
Yeah.
you want to have it in the inside, you have to deform that differential equation. Have to spin up the inside too, and that's why there's a heat in the inside too.
It's not inside. It's not depositing inside. I'm not
Well,
sure.
your initial part is on the outside.
Yeah, it's all on the side. Yes.
Right. So
Right.
the whole thing is going to be differential.
Sure.
So
And
you
therefore,
can-
you should
and
generate
if you want to
magnetic
spin
field.
up the interior, you have to deposit heat as well. Unless it's magnetized.
But most of the people do that.
Yeah, most people do magnetized.
So we haven't done any of these things.
So you were planning, just so I really understand, so that yes, the white dwarfs always synchronize.
Outside.
In the simplest picture,
Yeah.
Sometimes depending on
well,
the
we just
composition,
no outside, not just outside. We just assume. Look, this is just assume. The whole star
depending on the
behaves-
composition, it takes a little bit longer or a little bit less long. So the period where it happens.
Yeah,
varies
the-
the composition.
yeah. So this
Right.
number, yes. Exactly. You ask me.
And this is recorded, right? Because I'm going to test this.
Yeah, so this curve has a range. I mean, there's uncertainty in the theory.
I'm going to test it at your 12-minute time.
4 minutes, I would say 80%, but this could be 60%. Who knows, right? This is uncertainty.
But not zero.
Yes, and that's life. So
Now,
okay.
But another question, so when you apply this to neutron stars, they're too strongly stratified?
Oh yes, yeah. I have for many years since my PhD thesis, I've been trying to sabotage LIGO. In a sense, because they like to have a clean two-point mass orbiting each other, nice waveform. So down so with Yanqing, we try to look at dynamical tides in the emerging white dwarf, try to see whether you can have a significant energy transfer from orbit to tides at when orbital separation is large. Right?
LIGO would love that.
Yeah.
And you can do so much mass processing.
Yeah, right. And so some of us have done this kind of problem. Andres Reisner had taken with Peter Goldway, Strata, so basically looking at different kind of oscillation modes of neutron star. The current result is that if you are looking at 10 regular neutron star, 10 kilometer radius, the effect is small in the sense that the phase error you induced by transferring energy from orbitals to the mode, it's less than 1 radian. So therefore, it's okay to treat them as a point mass.
Well, why white dwarfs then?
But finish. If you take a 15 kilometer neutron star, then that's becoming very interesting. If you give you 15 kilometers,
The puffiness matters.
yeah, puffy thing, then the tidal effect will affect the phase. Okay, and so there's still some interesting things here. Now for white dwarf, it's clearly more important because it's much bigger. So the decay is slower. Optical decay is slower, right? So that's why you can stay in the resonance for a longer time. Whereas for neutron star case, the optical decay very fast. You don't stay at resonance for a long time. So okay, so that's the. Let me just summarize this white dwarf story, right? The dynamical tides of white dwarf binary involves excitation, continuous excitation, the gravity waves, it's outgoing, eventually dissipated. We think this is the right way to think about this. The approximation involved in this, of course. And the white dwarf will be synchronized mostly prior to merger, but not completely. Therefore, there's always tidal heating in the white dwarf, and the heating may be very important. And stay tuned.
When you say not completely, at the time that they merge.
Well, not completely in the sense that there's always, because always decaying.
But
so
I can't extrapolate in my head from your graph. So you're within 1% or within 0.1%?
Well, all I'm saying is that if it's completely synchronized, then there's no heating.
No, of course.
But there's always a heating, and this heating is increasing.
But there's always heating because all is always changing.
Yeah, that's right. Yes, not heating.
So at the contact is editing.
If you're very close to synchronize, you don't heat so much anymore, right? Because then you have your omega S over omega.
Well, but this takes that into account.
Yeah, but if that becomes 1%, the tidal.
Yeah, this includes that. That's why
Yeah,
it's smaller.
Right.
This includes too. Okay, so let me move on to. Because I have 3 topics. Let me move on to another thing. I'm going to try to do it faster. Okay. So this is an interesting system. Two main sequence stars orbiting each other in an eccentric orbit. Okay, this is discovered by Kepler. So it's an apex star, 2 solar mass, also 42-day orbit, eccentric, face-down orbit. So the pericenter separation is 6 stellar radii. Okay, the corresponding frequency at the pericenter, orbital frequency at the pericenter is about 20 times the mean orbital frequency. Okay? So here is the light curve. You see all these spikes in the orbital period. These spikes correspond to the pericenter passage. So at pericenter, the star is highly distorted. You get ellipsoidal variation and also reflection, irradiation of the binary. Okay? That's what's causing the spikes. But the interesting thing for this system is that if you subtract all these parallel spikes, you still get a lot of variation here. You can see variation here. If you do Fourier transform of this light curve, you find many peaks, well-defined spikes. Okay? And they find 30. The Kepler team found 30 pulsations, well-defined high significance pulsations. 21 of these are integer multiples of orbital frequency, the mean orbital frequency. So you can list the third frequency divided orbital frequency ranging from 22.4 to 91. Okay. So the question is, what are these oscillations? Okay, obviously, it's tidally induced because you're in orbital frequency. Okay, but then the question is how. Okay. Time, let me this is propagation diagram. The star supports gravity wave, G mode, cavity here, there are G mode, gravity wave, intrinsic modes inside the star. Okay? So you can look at straightforward way, look at the tidally forced oscillation. You can translate that into the flux variation. Okay? So here's what you get. So here it's basically the flux variation induced by the tide. Right? The tide induced makes the oscillation. I should skip a little bit. You can either, of course, when you have eccentric orbit, you can decompose the tidal force in the orbital tidal potential into harmonics of the orbital frequency, right? So n times orbital frequency. So each harmonics will induce forced oscillation. And so this is the flux variation, the function of this harmonics. And so this dotted points are calculation, prediction, for n equals 0, n equals 2 modes, and red points are theta. Okay. The bottom line of this thing is that most of these oscillations, this variation detected here, can be explained by n equals 0 modes, tidally induced. The reason is n equals 0 is because this is a phase-down binary. So n equals 0 corresponds to basically the changing effective area, projected area of the star from where you see it. Whereas n equals 2 modes is just you have a football rotating, you don't change the area, therefore it's hard to see. So that's why n equals 0. So most of this can be explained by n equals 0 modes. The exception is this 90 and 91, because they have very high amplitude. And in order to explain this flux variation of this, you have to have a very close resonance. Namely, you have to say that we have an intrinsic mode of the white dwarf with n times some integer, n happen to be 90 or 91. 90 times the output frequency equals the intrinsic frequency to high precision. Okay, to less than n values, 2 or 3. What is this? So then the question is, what's so special about 90 and 91? Why is that there are many other things? The other things. Why is that you don't see anything here? You only see this, the highest is 90. What's so special about it? At least that's, for us, that's the main interesting thing about this. Okay. Now, you can't completely rely on coincidence. I'll explain why. Right? Because you could just say, oh, maybe it's a coincidence. Just happen to be, you have a mode, happen to sit there with equal to 90 times the orbital frequency. Right? That's not possible. Let me explain why. So let's consider a mode very near a resonance. So intrinsic mode frequency equals n plus epsilon times orbital frequency. Okay. Now, by chance, if you just rely on chance, coincidence, then the probability that this epsilon is less than some number, say 10%, that's roughly twice the 2 epsilon 0. Right? So 20% given mode. It's not so bad because it's not so bad, right? So 20% is not so bad. In particular, if you think about there are many modes within this frequency range. So that's why in this plot, we not talk about it, but some of these are higher. Because there are so many modes, some of them just by coincidence they can just be close to resonance, to within 10%, and that will be enough to give you this variation. Okay. The exception is this 1991 because they have very high amplitude, and it's so high amplitude that the mode energy is actually large. So this mode has large energy, so therefore what's happening is that you're transferring energy from orbit to the modes, right? And in that case, when you transfer energy from orbit to the modes, the orbit is decaying. When you strike a resonance, right, you transfer energy from the mode. The orbit is shrinking very fast, so the orbit will evolve away from the resonance. So that's why you don't get it, because that's why the probability is much smaller if you take that factor into account. Namely, if this particular mode has a lot of energy, right, the dominant energy transfer, tidal energy transfer, then the probability is even smaller. Okay, so if you have epsilon less than 1, this is actually very small. So we think it's unlikely, very unlikely to just use coincidence by chance to say, yeah, you happen to be there in 1991. Okay? And the way you get this, we think, is that you have resonance locking. So let me explain how this works. Okay? Right, okay, so suppose you are in a resonance, right? You basically, the orbital energy is constantly being transferred from the orbit to the star, right? The orbit is shrinking. At the same time, when you excite the modes, right, you also spin up the star because when you excite the mode, you transport angular momentum also. So the spin angular frequency of the star is changing, and that means the mode frequency is also changing. Right? The mode frequency depends on the spin frequency. Okay? So when you have a resonance, both things are changing. The orbital frequency is changing, the spin frequency is changing. So therefore, right, you can, okay? So, so at resonance, you have this relationship of the mode frequency equal to integer times omega. This resonance you can stay in the resonance if this derivative equals zero. This ratio is not changing. In other words, at the resonance, both the orbital frequency and the mode frequency are changing, but they will stay in the resonance, will be locked if they're changing at the same rate. Right? They will change at the same rate. So two things are happening in resonance. Orbital frequency is changing, and the second thing, the mode frequency is changing. Both changing. So from this, you can easily derive a critical condition for this resonance locking that you will number the critical n. Only one n. The only one n is satisfied, and that n, capital N, depends on the orbital separation moment inertia of the star, reduced mass, right? And it depends on how the mode frequency vary as a function of the spin frequency. You put in the number, you find 130 within the, okay, to the extent you know the number. Okay, so that's the critical number. That's a critical number. So what it says is that if you have a resonance at n greater than nc, then the orbital decay rate is too large compared to the rate at which the mode frequency is changing. Therefore, you don't stay in the resonance what you want. If n is less than the critical number, the orbital decay rate will be slower. The spin rate is too high. Therefore, you also don't stay at resonance what you want. And only at this particular n can you have resonance locking. Now, having said that, you may say, oh, that's bad because we have to fine-tune this n. We have to somehow be exactly at this n for it to be locked, right? But it turns out to be better than that because if you think about the star is actually evolving. This is the main sequence star. It's actually evolving. It's close to the end of the main sequence. So it's actually expanding. The star is actually gradually expanding. And so it's slowing down gradually, intrinsically. Slowing down. Okay? So the spin frequency is changing not just due to tides, due to binary, but also intrinsically slowing down. Because it's only by S star. It's negative. There is an intrinsic spin down due to stellar evolution, the expansion of the wind, stellar wind. Okay? So both contribute, both tides and the intrinsic torque, intrinsic spin down contribute to the spin evolution. If you take that factor into account, you can easily convince yourself that mode locking can occur not just at this particular NC, but can occur if n is less than NC. Okay, because they're both the two contributions to the spin frequency evolution. Okay, so resonance locking can occur if this n, if you are locked into resonance with n less than NC, then this can happen.
So what is the reason?
Sorry?
So you have two contributions to the
What's that?
Why are you saying that you don't need NC, but any is smaller than C?
Okay, so we can go through this math.
Well, any n, right? It depends on the stellar evolution, what n you then get, because it depends on how fast you're evolving.
Yeah, I mean, what I'm saying is, if n is less than NC, then you can, in principle, lock.
As long as you go fast enough before the
Yeah.
start.
Right. Okay, so we did that's next. I'm not sure what's answer.
But then isn't it fine-tuned? Because you can be exactly say this.
No, so this, if you just do this, then you have to fine-tune, because you have to say, okay, only when n is exactly equal to this, can you have locking? But now with this, which is very natural, with this you can lock in principle as long as n is less than nc. Okay, so we have to go through this. Okay, we did some numerical experiments. So here's, for example, is just looking at this combined system, how the spin evolved, how orbit evolved. So here is just the simplest system. Two modes, only two modes. And you can see initially this ratio, mode frequency divided by orbit frequency is 0.5, 89.5, or 84, and then lock. This mode is lock. They lock. And then after some time, this other mode is locked. Kick this resonance, kick out the resonance. And here's another more realistic example, many more modes. You can see the mode images. When the mode image is much larger than one, that means you are in resonance. So here you have mode in resonance. And then here another mode in resonance. Okay? And let me just finish by saying, like, so far I've been talking about single star, one star, right? One mode inside one star. For that case, in that case, you have this critical NC. If you consider two stars, this system happens to have two stars, very similar stars, right? If you actually consider very similar modes in both stars, resonance locking can occur in both stars. So one mode on each star. In that case, this number, the critical NC, will be divided by square root of 2, and that turns out to be 92. Okay, so it's very nice, I think, you know.
So that's a prediction that each star, one of them
so
is the 90, one is the 90.
what we think now is that one of this mode is in one star, the other one is the other star, because it's not possible to lock resonance in one star. It's very convenient. Anyway, so that's the story of this resonance locking. Finally, let me just mention, this is actually another important thing about the system. Actually, not actually. There are many other oscillations that we detected that have non-integer multiple of the frequency. What are they? Right, the question you ask, what are these oscillations? Why is that, right? The forcing frequency is always integer times the orbital frequency, right? We have elliptical orbit. But they do detect nine oscillations with non-harmonics, non-orbital harmonics. And one possibility is that this nonlinear mode coupling, basically you excite a mode, right? And then you have nonlinear three-mode coupling, decay into two water modes. And Jim Fuller looked at this table, actually, he actually found that, yeah, this number and this number equal to 91. Okay? And this actually was not noted in this discovery paper. We actually looking at it. So this is actually quite nice. It's actually, I know this is people studying nonlinear mode population during these days for white dwarfs. This is actually the very explicit evidence that there's nonlinear mode coupling happening inside the star.
Do you have a second example of that, or is that?
This is the only one. This is the only example. Okay, then you ask yourself, what happens to other things? Well, obviously, we can think that other non-integer modes are likely to be nonlinear mode coupling, which one of the water modes is invisible. You just have to see it, lower amplitude.
What about 44 and 40? Those would be right.
This is a.
No, but those are the ones that you don't need the resonance for, right? So,
sorry?
how about those are the ones you don't need the resonance for?
You don't need. This one you don't need resonance.
Well, they're.
Okay, this one you don't need resonance. We did not do. Yeah, they're pretty bright. We think you don't need the resonance.
So what's the intrinsic amplitude actually compared to the 991? Because they're lower order, so you need a fortunately lower amplitude to explain the density fluctuation.
this is your graph that basically tells you, right?
This is good. Yeah.
You
So-
see the much bigger difference.
No, no, we did not. I don't. We don't know how to approach this problem in a way to try to really compare. Always, it seems to be okay. Most of these are okay. Maybe you have better idea how to compare this.
He's asking which mode has the most energy. By far, so 99 first mode.
91, 99.
By
That has
far,
more.
that's
Yes.
much more energy.
That's much more energy. Yes.
Even the amplitude one can be stronger.
Yeah, I have more energy. Yes. Okay, so I think I want to. I'm done with this. So I have another thing, but I think I'll stop.
That's still a lot.
Sorry?
That's still a lot.
I'm ready. We time for one question, then we do the decision first. We can just move first. Yes, that's how we're going there.